All right, good day to you. Next set of lecture is on the rest of chapter 1. So first of all, we're going to be talking about uncertainty in measurement. So when you have different measuring devices, so sometimes you use a graduated cylinder, you might use a beaker, you might use a pipette, volumetric flask. So certain items have better accuracy at what they're measuring. Like for instance, that's one of the reasons why we don't ever use beakers to measure specific amounts of volume, because they aren't designed to have any level of accuracy. They're really just a container to do reactions in, not one to measure volume. So the items displayed on this slide are more often used for measuring amounts. Graduated cylinders, syringes, and burettes. You can measure a specific increment. So if you want, 5.5 milliliters, you can measure that out. When it comes to like a volumetric pipette or a volumetric flask, those types of items, they measure a specific amount of liquid very accurately. And balances as well go to a specific level of accuracy, and so it's important to record values to the digit that you're allowed to, and that'll come up as when we talk about significant figures. So when we talk about temperature, so we measure temperature, and temperature is really, so you put a thermometer in a liquid and it tells you a temperature. Well, what it is measuring is the average kinetic energy of the particles in that solution. So some particles might be going slower, some going faster, but the overall average is what determines what the temperature of the solution or substance is. Now, in scientific measurements, we use Celsius and Kelvin. Those are the two scales that we use. When we use Celsius, Celsius was and is based off of the melting and boiling points of water, and so thus you have 0 degrees and 100 degrees. It's nice firm numbers. When you use Kelvin, so that's the SI unit for temperature, and Kelvin is based off of gases, the behavior of gases, and we talked about that a bit in first year chemistry. But the idea of that is that there is no negative temperature when it comes to Kelvin. It is there's absolute zero, and nothing can be colder than that point, because, well, gases at 0 Kelvin don't move. There's literally no kinetic energy at that temperature. So being able to convert between Celsius and Kelvin is it's just kind of a standard. So you need to be able to do that. That's something that in first year chemistry you learned, and so just kind of remembering that if you have a temperature in Celsius, you just add 273.15 to it, or if you're in Kelvin, you would subtract that to get Celsius. Next, temperature scale, which in the U.S. you're probably most familiar with, which is the Fahrenheit scale. This, we don't actually use that temperature scale in science because, well, all the formulas, equations that we utilize don't use Fahrenheit. Fahrenheit is just, it's not very intuitive. Like when you convert to it, I mean, you're using a 9/5, then you're adding 32. It's just messy. So for the most part, we don't use Fahrenheit. Density. So density is it's a physical property of a substance. It doesn't matter if you have a lot of it or little of it. Density always stays the same for a pure substance. And density is mass over volume. You have learned about density since, I'm assuming, elementary school, but I'm sure it was at least introduced in middle school. All right, now let's talk about uncertainty in measurement. So sig figs, or significant figures, are an important component of when you do laboratory science, because your some things that you measure are only as accurate as the instruments that you're using. So you round, like when you do calculated values. When you take the final value that your calculator gives you, you can't take all those digits that are written on that calculator. You have to limit your final answer, your calculated answer, to how accurate your measured values were in the laboratory. So if your If your balance only goes to the tenths place, then final values can't go all the way out to the 10,000ths place or something like that. And we'll get into some practice problems relating to that. All right, some of the rules of significant figures include that, well, if you have any value that has digits, 1 through 9, then those are significant. You need to count those as significant figures. But it's the zeros where things start to get. That's where people find it challenging, is keeping track of what you can keep when it comes to zeros. So zeros between two significant figures are themselves significant. So if you have like a 305, the 0 in the middle would be significant. So that whole number would have 3 significant digits. Now, zeros at the beginning of a number are never significant. So if you have 0.0037, those zeros before the digits, they are not significant. They're really just a place setter telling you that it's a really small number. And another way to kind of think of it is you could rewrite 0.0037 as 3.7 times 10 to the negative 3. So you can write it in scientific notation, get rid of those zeros, and still just have those 2 significant digits that are really part of that value. And then the next, or the last rule related to zeros is that at the end of a number, they're only significant if there's a decimal point written at the end. So let's say you have a large number like 45,000. If you have just 45,000, so 45 and 3 zeros, only the 4 and the 5 would be significant. But if you had 4,500 point, so 45000 point, what that decimal is implying, it's implying that when you took this measurement and you got that value, you measured it all the way to that decimal point. So you would have 5 significant digits. And we'll do some practice problems related to this. All right, so significant figures, so that's when you're measuring and taking them, but they really apply when you're doing calculations, because you need to figure out, well, how many values can I take after my calculation, after I've done some type of math with these values. So when you're doing addition and subtraction, you're going to round to the least significant decimal place. So you line up all your values along their decimal, and then whichever value has the least decimals, then that's where you're going to do your cutoff with your final answer. And when it comes to multiplication and division, you're going to perform the multiplication or division, and more often, multiplication and division is going to be the operations that you're going to utilize. And so you're going to take a final value based on your least number of significant digits. So if you have a value that has 3 sig figs and one that has 4 and another one that has 5, well, your final answer that you take can only have 3 significant digits. And that's something that sometimes frustrates folks, because like my calculator gives me all these numbers, but no, you are limited by the measured values that you use. All right, next, just real quick, we're going to talk about the difference between accuracy and precision. So accuracy is how close was your value or your measurement to the true value, what it actually should have been. And then precision is how consistent were you in getting that measurement over time. So the proximity of several measurements to each other, and those are two. So obviously, being accurate to the true value that's good laboratory technique. But just as important is how consistent can you be in the laboratory as far as repeated trials and getting similar values. Because if a scientist gets quote unquote the true value only once but never can repeat it, that research will definitely be called into question. Because if you can only get it once, then was it really good science, or was it just a fluke? And it really makes you question the validity of the whole experiment. All right, dimensional analysis, and this is where we're going to kind of finish off. And dimensional analysis and kind of difficult to explain utilizing just the PowerPoint, so we'll go over this in class, but dimensional analysis is a great way to answer chemistry problems because even if you aren't sure what the final answer should be, if you know the starting units that you're with and the ending units of what your answer should be, you can often kind of work your way by determining the correct conversion factors to kind of move from one thing to another. So in this example, let's say you are given a value in meters and you want to convert to inches. Well, you're going to need some conversion factors, some relationships between um, inches and centimeters, as well as knowing the relationship between meters and centimeters. So dimensional analysis, you use the form of the conversion factor that puts the sought for unit in the numerator. So you want to cancel the units that you have and end up with the units that you want. So an example here, if you have 8 meters and we want to go to inches, first of all, we're going to use the conversion factor of meters to centimeters. And so we're going to set it up so meters on the bottom, centimeters on the top. And so meters will cancel. Then we're going to use the conversion factor between inches and centimeters. And so now centimeters will cancel. And then the only unit that's left is inches, and then you just do all the math properly. So you would do 8 times 100 times 1, and then divide that by 1 times 2.54. And yeah, that's what you got to do. And we're going to do some practice tomorrow. Thanks.